Hello and welcome to this video in which I explain how a chi-square difference test works in confirmatory factor analysis and structural equation modeling. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods such as structural equation models, factor analysis, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as courses that I offer through QuantFish. In this video, I want to show you how you can perform a chi-square difference test and under which conditions. And really this video is about two different issues. One is about what are nested models, because the chi-square difference test is applicable or applies to nested model comparisons of fit. And then second, the video is to show you how a chi-square difference test works. So how would you do it? So let's start with the first issue, and that is what are nested models. The chi-square difference test is suitable and is useful when you want to compare the fit of so-called nested models. So what are they? Here is a simple example of nested models. Here we have a factor model A, which is a confirmatory factor model with two factors. In this case, each factor has two indicators, so it's a pretty simple model, but the same principles apply to more complex nested models that have more factors or more indicators. And so in this factor model, in this standard factor model here on the left-hand side, we have the first loading of each indicator per factor fixed at 1 for identification, which is standard in factor analysis to provide a metric for the factors. And then the second loading here indicated as lambda 2 for the second indicator of the first factor, and as lambda 4 for the second loading of, or the loading of the second indicator on the second factor. Those loadings are freely estimated. So the parameters lambda 2 and lambda 4 here are free parameters in this model. We sometimes call this a congeneric factor model, where different indicators measure the same factor. In this case, for example, y1 and y2 are congeneric measures of f1, and then y3 and y4 are congeneric measures of f2 in this model. And so in congeneric models, the indicators measure the same factor, but they can have different loadings. So for example, lambda 2 could be different from 1, and also lambda 4 could be different from 1. For example, if the indicators differed in their scaling or metric, in their units of measurement. And so this is a general, so say, factor measurement model of confirmatory factor analysis. And now we can have more specific measurement models where we make more restrictive assumptions about the factor loadings, for example. And so one more restrictive model would be one where we assume that all the factor loadings are equal to 1, or we could say where we assume equality of the factor loadings, and we call a model like this a model of essential tau equivalence, where the indicators have equal loadings, meaning they have the same units of measurement. And that would, for example, be a plausible model if you had different indicators that were parallel tests, or test halves, where each test or test half is on the same scale. For example, the same number of points can be reached, or the same number of questions that are being scored. And so then it would be plausible that the indicators may have equal loadings, and so we might then want to test such a model as well. And so this model B with equal loadings, the model of essential tau equivalence, that model is nested within model A. It's a special case of model A that is more constrained. Model A, you could say, is the more general model, because it includes the case that lambda 2 and lambda 4 may be equal to 1, but they don't have to be equal to 1. They can be whatever they want. If they are 1 in the population, then in a given sample, they should be estimated to be close to 1, depending on how much sampling error there is, but they need not be 1.0, whereas in model B, they are forced to be equal to 1, and so that's more restrictive. So model B is more restricted than model A. Also, model B is more parsimonious, so say it estimates fewer parameters, 2 loadings less than model A, and so model B, so say, could only fit worse than model A, or maybe just as good, but it can't really fit better because it's more constrained. So it has more opportunity or more possibilities to fail, namely if lambda 2 is not equal to 1 or lambda 4 is not equal to 1, then model B would be misspecified. So it's a more restricted model, more constrained model. It has more degrees of freedom than model A, and it is a special case of model A because it follows directly from model A by imposing those constraints on the factor loadings. That's why the model B is said to be nested within model A. Model B has the exact same structure, but more constraints. Or you could say it follows directly from model A by imposing those constraints. It's a special case of model A. And so whenever you have something like that, where one model has the same structure as another model, but has additional constraints, then those models are said to be nested. And then in many cases, those models can be compared to one another with a chi-square difference test. So what does that mean? When we do confirmatory factor analysis or structural equation modeling, we usually use an overall chi-square test of model fit to test the absolute fit of a given model to our data. So for example, for model A, we would obtain a chi-square test to test whether this model fits the data. And for model B also we're getting a chi-square value. And then we can see if the model B fits the data. If the chi-square test is significant, then a model is rejected, meaning it does not fit the data. And now with the chi-square difference test, we can then also compare the fit of different models when they are nested, and we can look at whether model B fits significantly worse than model A. Since model B is the more constrained model, I told you earlier it could at best fit as good as model A, but typically it'll fit worse because it's more constrained. And so the question is that decline in model fit that we encounter with model B statistically significant? So does model B fit significantly worse than model A, or is the decline in fit or the increase in the chi-square, is it negligible, or is it not statistically relevant? So let's take a look at this for this example. I estimated those two models here for a data set in Mplus, and so model A yields a chi-square test of model fit in Mplus with a value of 0.131, 1 degree of freedom, and a p-value of 0.7179. So model A has an absolute fit that is really good. Model A is not rejected. The chi-square value is small, almost 0, 1 degree of freedom, and the p-value is high, 0.71 or 0.72, and so that indicates that the model is not rejected. The chi-square value is not significant, and so this means model A fits. So a two-factor model looks good for these data, at least in the congeneric case where the loadings can differ between indicators. And now we might want to know, is a model also reasonable that assumes equal loading? So a model of essential tau equivalence, or model B, and that would help us to make the model more parsimonious. So we would save 2 loading parameters that would no longer have to be estimated. The model would be simpler, and we could then also say these measurements are essentially tau equivalent and not just congeneric. So what does the fit look like of model B? Model B has a chi-square value that is 38.209, and it has 3 degrees of freedom and a p-value that is 0.0000 something. So that shows us several things. First of all, you can see the chi-square value is a lot higher than for model A. For model A, it was 0.131. Now it's 38.209. So that's an increase in the chi-square due to these constraints. In model B, I fixed lambda 2 and lambda 4 to 1. So to have all equal loadings, and that resulted in an increase in the chi-square value by 38 points, or a little over 38 points, and a difference in an increase in the degrees of freedom was 2 because there were 2 fewer parameters estimated. Therefore, model B has 3 degrees of freedom, whereas model A has 1 degree of freedom. So those two things we can see, first of all, and then also we can see that the p-value is not very favorable for model B. So model B would be clearly rejected already before doing a chi-square difference test in this example. So model B clearly doesn't fit, and that would already tell us that the second model B, that those constraints are not acceptable here. So these variables are not, at least not both of them, are not essentially tau equivalent. They don't have equal loadings. So in this case, you wouldn't even have to do a chi-square difference test because it's so clear that model B is rejected, whereas model A is acceptable. But to show you how this works for these two nested models, I also want to show you the chi-square difference testing, how it works. So the way it works is that we take the difference in the chi-square values for nested models. In this case, that would be taking the difference B minus A. So always the chi-square for the more constrained model is the one that is higher or at best equal to the chi-square for model A. So we always subtract the chi-square value for B minus, or we subtract the value for A from the value for B. So in this case, that would be 38.209 minus 0.131 is 38.078. That's delta chi squared, the chi-square difference value, and you can see that's almost as large as the chi-square value for model B. Then we also take the difference in the degrees of freedom. Again, B minus A, that's clear because you don't want to have negative degrees of freedom. That wouldn't make sense. So B has more degrees of freedom than A because B has more constraints. B is more parsimonious. So in this case, we have delta df, 3 minus 1 equals 2. That's the difference in the number of parameters between the two models. And then we look up the p-value for the difference. So we figure out what is the p-value for a chi-square value of 38.078 with 2 degrees of freedom. Now, how do you do that? That is something that many people find difficult to figure out. There are different ways that make it easy. One is you could just Google chi-square distribution calculator on the internet, and there are several calculators that allow you to determine the p-value for a given chi-square test statistic with given degrees of freedom. You just enter that chi-square value of 38.078, you enter the degrees of freedom, which here are 2, and then it spits out a p-value for you. Another option is to use Microsoft Excel or some similar program where you can just simply use a function that's called chi-square distribution right tail that Excel has, and you can enter those values, and then Excel will give you the p-value for the right tail of a chi-square distribution that is cut off by this chi-square difference value. So that's how I did it, and the p-value that I determined in Microsoft Excel is incredibly small, 0.00000 something, so definitely statistically significant, indicating that model B fits significantly worse than model A, and we already guessed that from the absolute fit value for model B, which was highly statistically significant also. So this is to say the conclusion: when the chi-square difference test is significant, it means that the more restricted model is rejected, or we could say that the more restricted model fits significantly worse than the more general model. Now, I also want to mention some caveats with the chi-square difference test. And so one is that the models have to be nested. So you can't compare just any models with a chi-square difference test. So there has to be nesting. And that's not always 100% clear cut whether models are nested or not. So that's sometimes a little tricky to figure out. So make sure when you apply this that your models really are nested. And then another issue is that the more general model, so in this case model A, should fit the data. So if already model A is rejected, then the chi-square difference test may be biased by the fact that model A already doesn't fit, and then it doesn't make sense also logically to test more constrained models. If the most general model already does not fit your data, then additional constraints could only make it worse. So you shouldn't really apply this when the initial model has a horrible fit. When that's already clearly rejected, then you should rethink your model A first before testing additional more constrained models. Also, one thing that can be confusing is when both model A and model B fit your data well. So let's say they both have non-significant absolute chi-square values for the test of global model fit, but the chi-square difference between them is significant. Then what do you do? That can be confusing because that would mean that B fits worse than A, but B also fits, or B is not rejected. So then would you not want to go with B since B is more parsimonious and it fits? So that's something that I also don't have a clear answer to, and that has puzzled me as well in my analyses. And I tend to think that if your model B isn't rejected by the absolute chi-square test of fit, then I would still go with model B even if the difference between A and B was significant, because that is kind of weird to say, okay, both models fit, but B is a little worse than A. I would then still probably prefer the more parsimonious model since it's not rejected based on the absolute test of fit. But that can happen, and so just be aware of the fact that chi-square difference values can be significant even when the absolute fit chi-squares for both models are not statistically significant. Also, some complications can arise when you have nested models that are nested, but the nesting is due to so-called boundary constraints. And one example would be in our two-factor model that I showed you here, when we constrain the correlation between the two factors to 1. That's often something that's of interest, where people want to know, is there discriminant validity between F1 and F2, and they want to constrain the correlation between F1 and F2 to 1 and test that against a model that leaves the correlation freely estimated. So model A would be one where the two factors are just simply freely correlated, as in our example. And then model B would be one where the correlation between the two factors is constrained to be 1.0. And clearly those models are nested, because then model B is a special case of model A where the two factors are perfectly correlated. However, a correlation of 1.0 is a boundary value of the admissible parameter space for correlations, because we all know that correlation coefficients can only vary between -1 and +1, and so 1 is exactly at the boundary, and so that causes some trouble for the chi-square difference test. Then it violates certain regularity assumptions of the chi-square test, and it may not be distributed as chi-square in that case, and so then some adjustments have to be made in that case, so be aware of that too. And so that applies, for example, when you compare a one-factor model to a two-factor model, because really what a one-factor model is, or how it can be re-expressed, is as a two-factor model with perfectly correlated factors. So that would be a situation where you would have to think about those boundary constraints and how you might potentially have to adjust the chi-square difference for that. Another occasion where you have to make adjustments is when you are using scaled chi-square tests. For example, when you have non-normal data and you use the Satora-Bentler correction, for example, for non-normality or other non-normality corrections, such as, for example, MLR in Mplus or ML whatever. then you have to take those scaling correction factors into account. And this is something then that you have to remember. Now, Mplus fortunately makes this very easy because it has a diff test option that you can use where it automates the process of applying or taking into account those scaling correction factors in the chi-square difference testing. So check out my video on that topic as well. On this channel, I have a video in which I discuss the diff test option, the automated chi-square difference testing for scaled chi-squares in Mplus. And so that's very convenient. That actually makes it easier than calculating the p-value by hand for non-scaled chi-square tests where you have to do that manually. So remember that when you have scaled chi-square values, then you have to take those scaling correction factors into account. I hope you found this video useful to learn about the chi-square and chi-square difference test as well as nested models. If you did, please subscribe to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.